Okay, we'll get started. Today, well, happy Friday. It's the end of week 8. We've got just 2 more weeks and then finals. Um, and so yeah, and so next week, starting next week, we'll do kind of randomization tests and bootstrap, and we'll do statistical inference using kind of computational methods. And in the the prerequisites for this class are like Stats 10, an intro stats class, or maybe AP Stats, and and I started doing this lecture, this review of statistical inference, just because in the past when I went over some of these topics, there would be a student who would kind of ask like, "What's a p-value?" and it was always kind of just like, "Oh no, you can't ask me that question." And so I just kind of wanted to make sure we're all kind of on the same page here as far as statistical inference. And so maybe you took Stats 10, maybe you took AP Stats, maybe you took something else at a community college or something. But I just want to make sure that we're going to kind of review some of these basic concepts of inferential statistical inference, and then and we'll go there. So I'm going to try to compress all of an intro stats class into one lecture. So all of Stats 10 into the next 45 minutes or so, which basically means I'm not going to do a very good job, but we'll just kind of blitz through it. Hopefully it'll jog your memory, or maybe you're already very good and familiar with everything. But anyway, we'll go through this review of intro stats. So probably one of the first things you covered was just like this talk of the mean and the median, and what are these? These are ways we describe the center. But I'm not sure if anybody ever told you kind of like why we use these things as measures of center. And so they might have said, oh, you find the mean by you add up all of the numbers and you divide by how many you have, and you find the median by sorting them, and then you start at the ends and you kind of work your way until you're at the middle. And that's true. That's how you find the mean, that's how you find the median. But conceptually, the median, what that does is it balances the number of points that are lower and higher. So you have the same number that are lower as you do the same number that are higher. And as far as the mean goes, it balances the deviations, the distances from the mean that are lower, and the deviations that are higher. And because you're trying to balance these deviations, if your data is skewed, your mean is going to get pulled in the direction of the skew. Because when you have a big outlier, you're going to have a huge deviation, and to kind of offset that, the mean has to kind of move to kind of shrink that deviation in order so that you don't have this extreme thing on the right. So here's just a simple example here. I've got a small data set with the values 1, 2, 3, 4, 10, and 10, and they're these dots on the number line, 1, 2, 3, 4, 10, and 10. The median will be at 3.5. We've got 3 values to the left of the median's in blue, and 3 values to the right of the median. Okay, whereas this red line is the mean is 5. Okay, and the mean being 5, we look at the deviations below. 4 is 1 below 5, 3 is 2 below 5, 2 is 3 below 5, and 1 is 4 below 5. So we have deviations on the left going 1, 2, 3, and 4. And on the right, we have the values 10 and 10. Each of them have a deviation of 5 above the mean. And if you look at the values 5 and 5, you have the sum of the deviations above are 10, and the values on the left, the sum of the deviations on the left are minus 10. So they balance each other out. Okay? And so you could imagine if you did have a value that was very extreme, very high, you would have a very high deviation, and to kind of balance out those deviations, the mean is going to get pulled in the direction of the skew. Whereas the median, it doesn't care. It just needs numbers. So whether it's very big numbers or very or not, values close to here, as long as you have 3 over there and 3 over here, the median is happy. So those are kind of your basic measures of center, the mean and the median. And then you probably talked about measures of spread. and we have the variance and the standard deviation. And the idea here with the variance and standard deviation is that they measure how spread out your numbers are or how close together your numbers are. And so, a smaller variance means the values are closer together. So the example I like to use is just imagine a second grade classroom and imagine the students in the second grade classroom. What are the ages of the students in that classroom? In second grade, pretty much everybody is 7 years old, right? Maybe some 8 years old. At the beginning of the school year, everybody's 7, and then as the months go by, some students become older. But pretty much nearly everyone has the same age, so you have very low spread as far as the numbers that you see. Okay. Meanwhile, if you go to, say, the DMV, and I guess this would be pre-pandemic, if you go to the waiting room of the DMV, which I guess for our international students, this is where you get your driver's license and stuff and fill out your vehicle registration. And so you have everybody, right? You have teenagers who just turned 16 and they're excited to get their driver's license. You have seniors, you have adults renewing vehicle registration. Sometimes they have to bring their children along. So you got old people, young people, everybody in between. You're going to have a very large variance in ages at the DMV there, okay? So the we can think of the definition of the variance as the quote-unquote average squared deviation from the mean, the squared deviation from the mean. And then the standard deviation would be the square root of the variance. And so if we kind of review the formula for the variance is 1 over n minus 1 times the sum of xi minus x bar quantity squared. And we can get to that by just first looking at xi minus x bar. That's distance from the mean. Xi minus x bar quantity squared would be the squared distance from the mean. And then if we were to add them up and divide by n, that would be the average squared distance from the mean. Okay? But if you do this, your value is going to be biased. This is going to underestimate the average squared distance from the mean. And so, so we divide by n minus 1. And I think you guys covered why you divide by n minus 1 in your 100B class or something. But, just kind of broad concept, if you knew the population mean mu, we would estimate the variance by doing distance from the mean would be estimated using xi minus mu. And if we square that and add them up and divide by n, that value would not be biased, okay? But the issue is we don't know what mu is, so we use our sample mean x bar instead. And because x bar is based on the sample, it's going to end up being right in the middle of our sample. It's going to be in the center of our sample. And so if we use x bar to calculate distances from the mean, it's always going to underestimate distances from the population mean, okay? Because the population mean might be not necessarily in the center of the sample. So using xi minus x bar is going to underestimate distances versus xi minus mu, okay? And when you divide by n minus 1 rather than n, that corrects for that kind of the fact that we're underestimating it. All right. Probably, another topic you covered in your intro stats class is the normal distribution. And so the normal distribution is this continuous, unimodal, and symmetric distribution. And all this means is values near the middle have the highest probability. Our peak is at the center here. And as you go high above the middle, above the mean, the probability goes down. And when you're very far above the mean, you have a very low probability. And the same goes in the opposite direction. As you go lower below the mean, the probability goes down, 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 down. And then when you're very far below the mean, the probability is very low. Okay, so this is our normal distribution. We might call this a bell-shaped curve because I guess you can imagine attaching a handle right here and then ringing this big bell or something. I don't know. Okay. The empirical rule says that you can get around 2/3, 68% are within one standard deviation of the mean. So here, this is the normal, standard normal. So this mark one standard deviation above and one standard deviation below the mean. And that's going to cover around 68%. When you go 2 standard deviations above and 2 standard deviations below, you get around 95% in the middle, okay? Around 95%, I guess more accurately, 1.96 standard deviations above and below. And then if you go 3 standard deviations above or 3 standard deviations below, you're going to get almost 100%, 99.7% within 3 standard deviations of the mean. And the normal distribution will play an important role later when we talk about the central limit theorem. So we have to talk about populations and samples. And so every research question that we have has an associated population. The population would be everyone who's relevant to answering the research question. The issue is that when you think of the population, it's always going to be too big for us to study it directly, or or we just don't know who's in the population. We just can't get a hold of everybody. So if our research question is some experimental drug, XYZ, is this effective at treating some mystery disease, JKL? The population would be everybody with this disease, everyone with disease JKL, and maybe we just don't know who everybody is, or there's too many people to track down. We just can't do it. So the population, the problem is we can't identify everyone. So this diagram is supposed to illustrate how we deal with this issue, and that is we select a sample from the population, and we study the sample, and statistical inference is the process of making conclusions based on a sample, and that we can kind of generalize or apply to the population. We can make conclusions about the population based on the sample. So this large, I guess, potato-looking thing is our population, and the idea is we can't study it directly, so we select individuals, and we put those into our sample. Okay, so our sample is just a small piece drawn from the population, and we're hoping that our sample is representative of the population. It's really hard to do this, though. Okay, now one method that should produce a representative sample is random sampling, but random sampling is not guaranteed to produce representative samples. It's a random process. Now, all of your textbooks, your IntroStats textbooks, always kind of glossed over this fact. They would just say, oh, imagine we have a random sample of 80 people. Imagine we have a random sample of 200 people. But the truth is getting a random sample is like this. It's truly a difficult task. We have kind of professional public opinion organizations that are trying to get people's opinions and thoughts about stuff, and they probably depend on phone surveys, but even that is not going to be a random sample, because if you imagine your phone ringing and somebody says, hey, can we get 10 minutes of your time for you to answer questions? Most people say nope, and then they hang up, right? So you imagine who is going to say yes. Who is going to say yes to that question? And are the people who say yes, do they represent the entire population? And the answer is maybe not, right? If one of the questions is, how trustful are you of strangers on the phone, that's not going to be, the answers you get there might not be reflective, right? Maybe the questions, if it's like, who are you going to vote for? Maybe not. Maybe people are, more or less reluctant. I don't know. So getting answers via phone survey, very difficult. I always I shake my head a little bit if I see somebody say like, "Hey, can you fill out my survey?" And it's just like this Google form, and they post it and they say, "Hey, we're trying to do some kind of survey. Can you fill this out? Send this to your friends." And I'm just thinking, this is not going to be even remotely close to being a representative sample. It's just going to be representative of probably friends and people you know who are going to be more similar to you than probably different from you. And you're just going to get, a bit of an echo chamber of responses here, especially if you just send it out to people you know, or, circles of people that you know. And getting a truly random sample, it's a hard thing. It's not a trivial thing. For the sake of the math and the sake of your intro stats examples and classes, we just kind of say, hey, we have a random sample, but you should always ask, like, is it reasonable to think that my sample is representative of the population? And this often gets obfuscated when you have a big sample, right? So a lot of times I see people, they go on a website, there's like Kaggle and there's like data, and they gather this, and it might be like scraped from, I don't know, Twitter or some other place. And I just go, well, how did they get this sample of data? Is it reasonable to think that this sample of data looks like some population or looks like some larger entity? And a lot of times I'm thinking, no, this sample is not a very good sample. It's not clean. So you should be critical of it. Yeah.
Random sampling is the logical equivalent of IID,
IID. Yes. Yeah. So independent, identically distributed. So the idea is when you select the individuals in your random sample, they all have they're all coming from the same population. So yes, that is kind of the idea there. Although IID, is they're similar or analogous, but I don't know. I hesitate to say it's the same thing. I guess in the most simplest of cases, yes, but always life is harder. So yeah, you could take an entire course on sampling methods. I think we have one here at UCLA. I think it's taught by Professor Cochran at some point. And you talk about all of these kind of strategies for how do you get a sample that's going to be pretty good. And it's not easy. And it's very expensive, or it can be, especially if you're dealing with people, right? I mean, even something, this is totally unrelated, but like imagine you're running like a lab and you've got like little mice in your lab and you're going to like run them through the maze and stuff. How do you get a random sample of mice? And you go, oh, I'm just going to reach into the cage and pull one out, okay? That's not going to be a random sample of mice. Why? Because the mouse you grab is more likely to be a slow, lazy mouse, unafraid of people and mysterious hands coming out of the sky than all the mice that ran away, right? When you reach into there. So you kind of have to, like, you would have to gather all the mice first, label them, put little numbers on them, 1 through whatever, 50 or something. I don't know how a lab works. And then you randomly select the number, and then you pick that particular mouse. But if you just say, I'm going to just reach into the cage and pull something out, that's not going to be random. And sometimes we don't even think about stuff like that, right? So, okay, but anyway, let's pretend we have a random sample, okay? When you take a random sample, we often calculate some kind of statistic on the sample, like the mean of the sample. But because this sampling process is random, if somebody else were to take a random sample and they calculate the mean, they're going to get a different value. Your sample mean and this other person's sample mean probably not going to be exactly the same. We would be surprised if your two sample means are drastically different, right? If somebody says, hey, I went around and I looked at 50 random gas stations in LA, and I looked at the prices of gas, and I don't know what it is, $4.58 or something a gallon or something. Somebody says my average was $4.58, and somebody else says, oh, I got an average of $4.55. You'd be like, okay, that sounds reasonable. But if one person says my average was $4.58 and somebody else says, oh, I got an average of $3.21, you'd be like, what? How could that happen, right? You would expect you'd say, are you sure you stayed in Los Angeles? Did you go to I don't know, Texas, or I don't know who has cheap gas, but certainly other places, right? So who knows, right? So you would expect certain values to be more likely. You would expect your sample means to be kind of similar, not drastically different. So when we talk about what's the distribution of all of the values for the sample mean, and we look at imagine all the different possible samples we could get, all the different possible sample means we could get, that's going to form the sampling distribution. The sampling, in our case, the sampling distribution of the mean, because that's what we're talking about. And so one way is we can kind of generate a sampling distribution kind of following this process. We imagine some hypothetical population. Wait, have I given you any view quiz answers yet? No, okay, before I forget, because I basically did. First answer is E. E as an elephant. E as an elephant is our first view quiz answer. E as an elephant. Okay, so we start off with a population. Now, for the sake of this example, let's pretend that our population is normally distributed, has its standard normal distribution, has a mean of 0, standard deviation of 1. We're going to say this is my population. And what I'm going to do is I'm going to draw random samples from the population. I'm going to calculate the mean of each of these random samples. I draw a random sample, I calculate the mean. I draw another random sample, I calculate the mean. I draw another random sample, I calculate the mean. I do this a bunch of times. Let's say I do this 1,000,000 times, 1,000,000,000 times. We're going to keep track of every single sample mean I get, and we'll look at the distribution of all the sample means. According to the central limit theorem, is when you're looking at the sample mean, that the distribution, your sampling distribution, is going to follow the normal distribution. It's going to have a mean same as the population mean mu, and its standard deviation is going to be sigma divided by the square root of n, the population standard deviation divided by the square root of your sample size. So just to kind of illustrate what's going on, the normal curve represents the population, and I'm drawing a random sample of 16 values from this population. I got negative 2.21, negative 0.84, negative 0.82. The values that I drew are shown on the bottom as a rug plot. These little red lines indicate the values that I've drawn. And the mean of all of these red values, or of all 16 of these values, is shown with this line here, and the mean is 0.092. Here's another random sample of 16 values, and so these are different values from the previous sample. And the mean, coincidentally, is very similar to the other mean at 0.096. So the previous mean was 0.092, this one's 0.096. Here's another random sample of 16 values, and these values, my values are negative 1.22, negative 1.15, etc., etc. These are the values, and when I calculate the mean, I got negative 0.197. Here's another sample of 16 values, another sample of 16 values. And so each of these things, we have, we're getting different values, different means. And I can repeat this process, and for this example, I did it 10,000 times. Every single time I'm drawing a random sample of 16 values from the normal distribution using R norm. And this is going to be my random sample, and I'm going to calculate the mean of my random sample, and I store the mean of my random sample. I'm going to store it in this vector sample underscore means. And so now I'm going to have 10,000 values representing the mean of 10,000 different random samples. And if I take the mean of all of those sample means, I get something very close to 0. And if I get the standard deviation of those samples means, I get something very close to 1/4. Okay? And that's, this is pretty much close to the population mean of 0. And this is, the population standard deviation sigma is 1. My sample size is 16. And so if I do 1 divided by the square root of 16, that's going to be a quarter. And indeed, that's what I get. And if I plot a histogram of my sample means, I get something that looks very much like the normal distribution. It's not exactly the normal distribution because, you know, this is the result of 10,000 random samples. If I approached infinity, it would be the normal distribution, but excuse me, we're not there yet. So, you know, if I did like 1,000,000 or 1,000,000,000, it would look a lot more like the normal distribution. But yeah, this is basically the normal distribution. We can see, you know, most of my observations are within, if each standard deviation is 0.25, I got 95% within 2 standard deviations of the mean between 0.5 and negative 0.5, and so on and so forth. A QQ norm of the plot shows that they all kind of line up, indicating that our distribution is normal. And so the key idea here is that, you know, according to the central limit theorem, that says if our sample size is large enough, then the mean of a random sample comes from a normal distribution centered at mu. Normal distribution centered at mu. Oh, does anybody have like a coin or a quarter? I'm going to need a coin in for my next example. So if you have one, oh, I appreciate it. But okay, so we have the normal, the central limit theorem says the sampling distribution will have the same mean as the population mean, mu, standard deviation sigma over the square root of n. Sigma over the square root of n, we call that the standard error. And because n is in the denominator, it's going to shrink as your sample size increases. Okay, and that I think makes intuitive sense. If your sample size is small, you only have 2 people in your sample, and we say, hey, you know, what's the probability that your sample mean ends up being very high? It's not that unusual to imagine just like, is it possible to get 2 random people where both of them are very tall? Sure, that could happen. Is it possible to get 2 random people where both of them are very short? That's also possible. But what if your sample size is 100 people? What's the probability that you get 100 people randomly selected where all 100 people are very, very tall? And that's very unlikely to happen because now you have to get all 100 people to be super tall or all 100 people to be super short. So that's quite unlikely to happen. So more likely, if you have 100 people, yeah, you're going to get some people who are tall, some people who are short, but it's all going to average out, and you're going to get something close to the mean. But anyway, the empirical rule says that 95% of the time, when you draw a random, the empirical rule says when you draw a random value from the normal distribution, 95% of the time it's within 2 standard deviations of the mean. And so now, when I draw a random sample, there's a 95% probability that the sample mean is going to be within 2 standard deviations of the population mean. Okay? So our sample mean, 95% of the time, will be within 2 standard deviations of the population mean. And we can take that and reason it and flip it around and say, whenever I see a sample mean, I can be 95% confident that it's within 2 standard deviations of the population mean. So when I observe a sample mean, I'm 95% confident that it's within 2 standard deviations of the population mean, or I'm 95% confident that the population mean is within 2 standard deviations of the sample mean. And we can use that to establish a confidence interval. All right? Back here, I said there's a 95% probability that when I draw a random sample, that it will be within 2 standard deviations of the population mean. Over here, I have to change my language a bit, and I say I'm 95% confident that the population mean is within 2 standard deviations of my sample mean x bar. So why do I have to change it from saying 95% probability to 95% confident? What's going on there? And this is where the coin comes in play. Does anybody have a coin? I thought I had a coin, but I couldn't find it. Nobody? You got a coin? All right. So the example here. I'll take it. All right, and I'll give it back to you. Thank you. Okay. So here I've got this coin, and I can say, hey, I'm going to flip it. What's the probability it lands heads? And you say 50%, right? 0.5. Probability that it lands heads, you'd say 0.5. Okay. No trick there. All right. So we'll flip it. Okay. I flipped the coin, and I'm going to ask, what is the probability that the coin has landed heads? And you go, what do you guys say? 1/2, maybe. Okay. All right. Now watch what I'm doing. I'm looking at the coin, and then I cover it back up. You haven't seen it, but I asked the same question. What's the probability that the coin has landed heads? And now you're just weirded out. The answer is that the last two questions, after I flipped the coin, it was nonsense for me to ask the question, what is the probability that the coin has landed heads? Because the coin has landed. There's no probability anymore. Probability is for uncertain events, right? Uncertain outcomes. And so prior to flipping the coin, it was fine for me to ask, what's the probability it will land heads? And 0.5 is the correct answer. But once the coin landed, there's no uncertainty. It either landed heads or it didn't land heads. It's nonsense to ask the question, what's the probability that it landed heads? Okay? You can say, because you don't know how it landed, you say, I'm 50% confident that it landed heads. I'm 50% confident that it landed heads. But we don't say there's a 50% probability that it landed heads. So, thank you for the point. It landed tails, by the way. Pass it back to right there. But so that's why we use the word confidence, at least for the frequentist view of probability. Now, the Bayesian view of probability says probability represents a personal belief, and so even though the coin has landed, we can talk about, and you can say there's, I believe, a 50% probability that the coin has landed heads. As it feels a little bit strange, at least for that example. It makes more sense in other examples that we can talk about. Okay. So anyway, that forms the foundation of the confidence interval. And so we say, I'm 95% confident that the population mean mu is within 2 standard errors of the sample mean x bar. And in this case, the population mean mu is a fixed value. There's no uncertainty. It's either in your interval or it's not. We can only just be 95% confident that it's in our interval. The issue is we don't know what the population standard deviation sigma is. So we use S as an estimate, which is a reasonable thing to do, but it introduces additional uncertainty. So to fix this issue, we use the t distribution instead of the normal distribution. And that means instead of using 1.960, we use a slightly bigger number. The other way we do inference is with hypothesis testing. Okay, let me give you another view quiz answer. Second view quiz answer is C. C as in cat. C as in cat. Okay, and in hypothesis testing, what we do is we create a null hypothesis, and we imagine a hypothetical population with a hypothetical mean and standard deviation, and we perform calculations under this hypothetical situation. And we ask, what's the probability that such a population could produce the random sample that we have? And so, for example, let's just talk about a simple t-test for 2 independent samples. And we use that to compare the means of 2 samples, and we ask if their respective populations have different means. So imagine we went to a second grade classroom, we gathered a random sample of boys, random sample of girls in second grade. We calculate the heights of the boys in second grade, we calculate the heights of the girls in second grade, and we ask the question, in second grade, so this is like 7-year-olds, are the heights of boys and girls, could they be the same or are they different? Okay? And who knows, okay? The null hypothesis is going to say something like there's no difference. There's no difference between the two means of the population. So if you were to measure the heights of all second grade boys and all second grade girls, and you got the mean of the entire populations, you would find the same mean, okay? And that when you take random samples, let's say you got a random sample and the height was this number for the boys, and the random sample, the height was, slightly different for the girls. We're going to just say that difference you saw, that's just because of random sampling. It's not because the populations are different. It's just when you do random samples, you get bigger and smaller numbers. Any difference we observe is just due to sampling or experimental error. The p-value is the probability of observing the data we got, or something more unusual, something more extreme, under the assumption that the null hypothesis is true. So just to kind of keep expanding on this, just imagine two hypothetical populations, and we're saying under this hypothetical situation, the two populations have the same mean of population 1, mean of population 2, they're the same. And when you take a random sample from population 1, you expect, and a random sample from population 2, we expect the means of your samples to be approximately equal. Maybe they're not going to be exactly equal, but overall, we expect the sample means to have a difference of 0 or something close to 0. And if they're not exactly equal, you get some difference between them, we want to know, is that difference significant? Is it significantly different from 0? And so we're going to figure this out by getting a p-value. We're going to ask, could this thing have happened by chance, or is it because of something else, right? So we're going to say if the two populations do have means that are equal, that is, that the null hypothesis is true, what's the probability that we would just get this kind of data from random sampling, from random chance? So our null hypothesis would be something like mu1 is equal to mu2. If you collect your data, let's say your x bar 1 is 10 and your x bar 2 is 12.5, 12.5. And this is a typo. It says, is the observed difference of 2? It should say 2.5 significance. Is your observed difference of 2.5 significant? Okay? And the answer is it's going to depend, right? It depends on the standard error. Let's say all of the values inside from sample 1 are very similar to each other. You got like 9.9, 9.8, 10.0, 10.1. Okay? And all of the values in sample 2 are very close to each other. 12.5, 12.4, 12.6, 12.3, things like that. Okay? And so you have a very small standard error. This difference of 2.5 would be considered significant. Okay? On the other hand, if sample 1 had values all over the place, you had a value of 10, but you also had 15 and 3 and 7 and 21, and then you look at and the average happened to be 10. You look at sample 2, the values are also all over the place. You got 2 and 8 and 7 and 16 and 5 and 23 and 22 or whatever, and the average happens to be 12.5, you're more likely to just say, well, you know what, the values are quite all over the place, and therefore this difference of 2.5, that could have just been a result of random sampling. Okay? And so it depends on how much variance you see within your samples, whether that difference of 2.5 would be considered unusual or not unusual. Okay? We would say this difference in one case, we would say the difference of 2.5 is significant. And in the other case, we would say the difference of 2.5 is not significant. And so when we calculate these p-values, it's, just the probability of getting our data or something more unusual if we assume that the null hypothesis were true. We compare it to some arbitrary value, alpha, to decide if the p-value is large or small. And if the p-value ends up being small, the threshold is usually something around 5%, we'd say the data we have is unlikely to happen if only source of variation is random chance, right? It's kind of like if you flip a coin 30 times, let's say you get heads 3 times out of 30, right? And somebody says, do you think something's wrong with the coin? Do you think they're cheating when they told me that they got 3 heads out of 30 flips? And you'd say, yeah, I think something's wrong with the coin, or I think they're cheating. Why? Well, because they say, couldn't it just have been random chance? Like, is it possible to get only 3 heads out of 30 flips to be heads? Is that possible? It's possible. It's not impossible that by random luck you get 3 heads out of 30 flips. But it's very unlikely, right? We just intuitively, we know when you flip the coin 30 times, you should get something around 15 heads. And getting 3 heads is this very unlikely thing. And so the fact that somebody got 3 heads out of 30, we either have to say, well, wow, we were really lucky, and that's why we got this. Or we say, you know what? The reason why we're getting 3 heads out of 30 is because the only thing at play is not just random luck. Something else is going on. Either they're cheating when they're flipping the coin, something's wrong with the coin, something's going on. That's why I'm getting 3 heads out of 30. It's not just that I got really, really, really lucky. That's what we're saying when the p-value ends up being small. On the other hand, if the p-value ends up being large, let's say you flip the coin 30 times and you get heads 13 times out of 30, okay? Now, if it's a fair coin, we expect 15 heads out of 30, and we got 13 heads out of 30. So we go, oh, 13 is less than 15, therefore, something's wrong with my coin, I'm getting less. But we'd say, no, that, getting 13 heads out of 30 flips, that's not that weird, okay? It could very well easily happen, even if it were a perfectly fair coin, just by a little bit of random luck, you could easily get 13 heads out of 30. That's not that unusual. So in that case, we would not reject the null hypothesis. We would not say that something else has to be causing the reason why I'm getting only 13 heads out of 30. Now, it doesn't prove that the coin is fair. It doesn't prove that the null hypothesis is true. It's just we're saying we could get this data from random chance. And we're not ready to eliminate that possibility that it was the result of random chance. Okay? It could be that cheating is going on. It's just not enough to really cause suspicion here. Okay, so in your intro stats class, all of these hypothesis tests relied on a sampling distribution defined by the central limit theorem, and that follows the normal distribution. And we call these parametric hypothesis tests because, we're using these parameters here to define our distributions. Next week, we're going to do randomization tests. And randomization tests say there's basically, we're not going to be using the central limit theorem. We're not going to use these parametric distributions, but we're going to just use randomization. And we'll use the computer to simulate the randomization. But before we get into that, because it depends on this concept of exchangeability, we're going to just do a quick review of data collection and how that works. I gave you 2 answers so far. All right, let me give you your last answer. Last answer today is B. B as in bear. B as in bear. All right, so this is just some silly example that I took from some handout. And we're going to say, a dentist wants to know if a daily dose of vitamin C, so some vitamin C supplement, will result in fewer canker sores than taking no vitamin C, okay? And so our first example, we say, all right, the dentist finds all patients with appointments in the first 2 weeks of December to participate in our study. We have those who, we ask them, do you take some kind of vitamin supplement, and do you take vitamin C supplements and stuff? And those who don't take vitamin C supplements. And then we look at the 2 groups. We say, how many of you have canker sores? How many of you haven't complained about it and stuff? And then we do our comparison. We find out there is a significant difference in the proportions. Those who take vitamin C have fewer canker sores than those who don't. But what can we conclude? Well, the issue is this is not a random sample. We selected patients within the first 2 weeks of December, so it's not a random sample. We can't infer to a larger population. And there's no random assignment of treatments. We just said who takes vitamin C, and basically, if somebody self-selects and says, I'm going to take vitamin supplements and somebody else doesn't, there might be other inherent differences between these two people. Like they might have different lifestyle choices and things like that. And so there could be a bunch of other stuff going on that's responsible for the difference in canker sores, not just the fact that some people are taking vitamin C and some people don't. And so as far as we go, all we know is that for these patients, those who take vitamin C have fewer canker sores than those who don't. We can't generalize to a larger group, and we can't draw any kind of cause and effect conclusion because it was an observational study. All right, what if we do the same thing? We select patients from the first 2 weeks of December, and then we do random assignment. We say some of you have to take vitamin C, some of you are not allowed to take vitamin C. You must abstain from taking vitamin C. All right, we go through the analysis, we find a difference between the two groups. What can we conclude? Well, again, it's not a random sample, so we're hesitant to generalize to a bigger population. But because we did random assignment, we might be able to draw a cause and effect conclusion. We can say, well, as far as these two groups go, those who took vitamin C and those who were abstained from taking vitamin C, there's no real difference between these two groups other than the fact that these ones took vitamin C and these ones didn't, because we randomly assigned them some to take and some didn't. So the fact that we got a difference, we can attribute that difference to the treatments. We can attribute it to the vitamin C or lack of vitamin C. But again, we don't want to generalize to the population. Okay? Over here, this time we're going to say we get a random sample of patients, dental patients somehow, and I don't know how we did this, but somehow we got this random sample, but it's an observational study. And so what happens here? Well, we can now generalize to the larger population of, I guess, all dental patients in the town. Okay? So you have to think of what your sample is representative of, or what it's a random sample of. And in our case, it's a random sample of dental patients in the town, so therefore we can generalize to the population of all dental patients in the town, which may or may not be reflective of all people, or all dental patients, period. So you have to say, well, what is it reasonable to think my sample will generalize to? And that's what you can kind of generalize it to. But again, it's an observational study. So even if we observe a difference, all we can do is we can't make a cause and effect conclusion. There could be other confounding variables. There could be other things responsible. Okay. Last example, we're going to have random sampling and random assignment. And if we have random sampling and random assignment, then we can generalize to a population because of random sampling. We can also draw a cause and effect conclusion because of random assignment. Okay? So we can say, so that's what we have, right? If we can generalize to a bigger group, great. The issue is this situation where you have random assignment and random sampling and random assignment. This never happens in real life. Okay, either you generally have to settle for a random sample, or you have to settle for random assignment. You're rarely going to get to do both, because anytime you have an experiment, you have to get patient consent to participate in your experiment, because you're going to tell them what to do, and basically as soon as if somebody declines, you no longer have a random sample. Okay, so you might have selected people randomly, but as soon as somebody declines and says, I don't want to participate in this, that's not going to be a random sample anymore, right? And so you might still be able to say, well, even though I don't have a random sample, I have reason to believe that my sample is representative of the population, and therefore I'm willing to generalize my conclusions. But you could also be wrong there. Okay, anyway, that concludes our review of intro stats here. So we'll end here for today. Have a good rest of your day. Have a great weekend. We'll see you Monday, and we'll look at statistical inference using randomization. So we'll see you then.